All right. So let me give you one last puzzle, because it looks like we're almost done, but we're missing one little piece here. So let's imagine that you're designing a fingerprinting authentication system. And you train your system with a fancy machine learning algorithm, and the probability of wrongly authenticating, meaning that I'm using my phone and there's a 1% chance that my son is able to log into my phone. But the probability that it's correctly working for me is 60%. So it takes me several tries to actually unlock my phone using either a Touch ID or Face ID. So the question to you is this a good system? Is it acceptable to have a 60% probability of correctly authenticating and a 1% probability of wrongly authenticating? So is it a good system, yes or no? Okay, there seems to be at least a mini consensus that it's a bad system, and that's probably correct. But my answer to you is that, well, it's a bit more subtle, actually. It depends. If you work at the Georgia Tech Research Institute and you're doing work for the Department of Defense and it's classified, then it actually might be okay to have a system like that. Because it's very unlikely that you allow someone who's not supposed to access the system to get in, even though you could argue 1% might still be too high. And the point is that it's more important to you that bad people don't get in than to make it convenient for good people to get in. But however, if you're Apple and you're designing a phone, or you're Google and you're designing a phone, user convenience matters. Your end users are not going to activate that feature if it's a pain and they have to click on the phone 5 times before they get in. And so whether your system is actually doing well or not depends on a metric that you have to introduce to capture how well it does. All right, so specifically here in the context of the authentication system, there is a function that tells you whether it identifies the biometric fingerprint, for instance, correctly or not. And how you measure that matters, and the value you get matters to decide whether your system is working well or not. Okay, so the reality is that there is an application-dependent cost that we have to introduce, and that cost has to affect the design, because what is an acceptable design will depend on that cost. Okay, and so the last thing that we're getting at to talk about supervised machine learning is that complete model here. That is the model we've introduced before. So it has a data set, which we assume is generated ID from an unknown distribution Px. It has labels, which we also assume are generated according to a conditional distribution P of y given boldface X here, which says that the labels can be noisy or maybe there is no exact ground truth. There is a set of hypotheses that explains the kind of models that we're willing to use to find that unknown function f that we're after. There's an algorithm that is able to come up with a model, but most importantly, that algorithm outputs a good model, and how good the model is a function of a loss function. Okay, and so the loss function, generically speaking, can be introduced as follows. It's a function L, and the function L allows you to compare 2 labels. Okay, so it captures the cost of making a prediction. So the way you would use L in practice is you would say, okay, I'm going to use the loss L to compare the label that I predict on an unseen point using the model G that I've learned, L of G of X, versus the true label. Okay, so this L of G of XY is the cost of predicting the label Y as G of X using our model. Okay, and so you can imagine, depending on what you put behind L, you're going to get very different results because it's going to affect what we mean as a high cost and what we mean as a low cost. Okay, so all of that now is enough to talk about learning effectively in a sound mathematical way. We have a way to describe how our data is generated. We have a way to define how our labels are generated. We have a way to define what our models are. And we have defined that there's an algorithm that is trying to minimize effectively a loss function to find a good model. So with all that in place, we can now talk about learning. So before I move forward, any questions on this? All right. So don't hesitate to ask. I'm more than happy to deviate a little bit from my plan here to clarify things. One thing I want to discuss very briefly with you here is, and it's in part motivated because I saw that call for proposals a few days ago that was challenging that ID assumption here. So we haven't done any meaningful mathematical work at this stage, but I think we can still try to think about why this ID assumption matters. So when you say that the data is generated ID according to a distribution Px, what you're implicitly saying, and that will turn out to be important in our proofs, is you're saying that somehow the data set that you're getting is representative of the universe. If your data were not ID, that would mean that somehow your data set would be extremely biased towards certain parts of the universe. So if I talk about, cats and dogs, imagine that I don't sample all cats and all dogs equally. Okay, I only sample Chihuahuas and I only sample Siamese cats. So then it puts me in a situation in which I can't quite distinguish all cats and all dogs effectively, because my initial data set was extremely biased and was not sampling all cats and all dogs ID, but was sampling some cats and some dogs only. So that ID assumption is actually something quite fundamental in learning, and there's no hope to learn how to generalize to unseen pictures of cats and dogs if you've never seen a picture, of a fat cat. You will never be able to predict that a fat cat is a cat if you've never ever seen a fat cat. So that's kind of what's buried behind that ID assumption. So there's a lot of subtle aspects behind that model that really do matter if you want to talk about learning. All right. So let's try to talk about, how we can now, having that model or that abstract conceptual framework to talk about supervised learning, how can we use that? So what is a supervised learning problem? I'm first going to define it by why it's not. Okay, the supervised learning problem is not about memorizing. Okay, so our goal is not to find an hypothesis H in the set that accurately assign the values to the elements of the data set, because we have the data set. So if we have the labels, we know what are the values assigned to the points. So if we were to just create a function that only has the purpose of explaining the data set, we have it because we have the data set. But that would be memorizing, that would not be learning. Our goal is really to find the best model H in our hypothesis set that is able to accurately predict the values of sample that we have seen. You have a data set of cats and dog pictures, but I'm giving you a new picture that you have not seen before, and you want to predict the label of that picture. So there are many things you can do to formalize that problem, but one very natural thing to do if you have access to a loss function is to compute what's called the empirical risk of an hypothesis H that you have selected on your data set. It's also called in statistics the in-sample error. And so what it is, and it's a quantity that I will denote by R hat n of H. It's my notation to remind you that it depends on the number of points in the data set through n, and it's an estimate somehow. That's why I put an at, and it's evaluated for a specific model. What it does is it computes the average of the loss functions evaluated between the prediction on the sample point xi and its true label yi. Okay, so it's an average of a loss between the prediction that you're making of the labels of xi and what you know is the true value yi because you are given the data set. Okay, so that's what the empirical risk is. Okay, and it's a very reasonable quantity to study because that average loss is something that you can compute. If you know the loss function, you have the data set, you can in principle compute that. There's absolutely no problem there. Okay, now computing the empirical risk in itself is not interesting because it only tells you, okay, you have a given model that is, reasonably good or bad at estimating, at explaining your data set. But the point of supervised learning, as I've emphasized before, is to generalize. What it means that what we care about is not the empirical risk. What we care about is another quantity that I will call the true risk. Okay, so true risk versus empirical risk. The true risk is also called the outsample error in statistics to indicate that it's going to be an error on samples you have not seen. And it is defined as follows. It is the expected value over x. Remember, x is a data point that I generate according to px. Y is the associated label that I generated for my feature vector x. It's the expected value of the loss function evaluated between h of x and y. Okay, so I think it's easier to understand what's going on here if I write explicitly what is the expectation. Okay, by definition, the expectation is the sum over all possible feature vector x, the sum over all possible labels y that I can assign to the feature vector of the probability of generating x, the probability, I'm putting a bar just to indicate that it's a dummy variable here, Py given x of y given x of the loss function between h of x and y. Okay? So that true risk is a quantity that exists if we agree with the model or the framework that we have that says that there is a px and a py given x. We can compute this. And what it's measuring, it's saying, well, now that you have a model H, if I give you an unseen sample, it's generated according to px. It has a label generated according to py given x, and I'm averaging over all possible values I can generate. Okay, so the true risk is representative of your ability to generalize because it's computed based on things you haven't seen, whereas the empirical risk is computed based on the data that you have. Okay, now, because you can compute the empirical risk, you can imagine that you can use the value of the empirical risk to compare different models. And then your algorithm is going to try to give you a model that has a low empirical risk. But the question that it raises is whether the empirical risk that you have is actually representative of the true risk. Again, the empirical risk you can compute. The true risk you cannot, because you don't even know what is px, what is py given x. Okay? So a lot of the questions in statistical learning theory are exactly about this. They're trying to explain under what conditions it is possible for empirical risk that you can compute to actually be representative of the true risk, which is what you care about. Okay? So slightly more formally, these are the questions we're going to try to answer together. Question number one, can we generalize? And I apologize, there's a small typo here. Can we generalize? What it means concretely here is it means that if you have a given hypothesis H, is it possible for the empirical risk of H to be close to the true risk of H? The second question is, can we learn well? Okay, even if we say yes to the first question, it's not enough. Can we learn well? Meaning that what we care about is not just having a model that tries to explain cats and dogs, right? I could give you a function that just tries to do things randomly, right? So every time I get a picture, I randomly decide whether it's a cat and a dog. The true risk of that function is going to be very bad, and my empirical risk is going to be very bad. So it's going to look like, indeed, I generalize well, but I generalize, but I don't generalize well in the sense that my risk is really bad. Because what I have not tried to do is I have not tried to give you a good model. So ideally, what you would like your algorithm to find, you'd like your algorithm to find an hypothesis or a model that I call H sharp here, which is the one in your class that has the minimum true risk. But the big challenge, if you're following me, is that we only have access to the empirical risk. And so the best model that we can identify is the model that minimizes the empirical risk. Okay, so I want you to really understand the difference between H star, which is the model that minimizes my empirical risk, and that's something I can compute from the data set and from my class H that I've fixed, versus H sharp, which is the best model in the sense that it would have the best true risk, which I cannot compute. Okay, so learning well would be being able somehow to figure out that H star is actually close to H sharp. But proving that, as we'll see, is not that trivial. So the first question we'll answer is when is, it is true that the empirical risk of H star is close to the true risk of H sharp. And of course, one of the lingering questions is, can we make the risk actually small? And the reason that question is different from all the others is, remember the discussion we had about the dress. We could not agree whether the dress was blue and black or white and gold. And so what that means is that you have to give away with this idea that you can design machine learning algorithms that have zero risk. You have to embrace the fact that the goal of machine learning here is to do something that's good enough. And in general, you will never have zero risk. Your risk will be non-zero, but your goal is to make the risk as small as possible. And we will explore probably next week, what is the best thing we can hope to do given a supervised learning model.